The chat hear me okay? Wonderful, thanks. I apologize for the delay. I've been running behind because I have been finishing up the exam and double checking all the wording on it to make sure that it's as clear as possible. Okay. Why is this not? Oh. All right. So, wrong one. Seating survey. Section 4, ILC 118. So it is still my plan to move the Friday's homework to next week. I know I promised that I was going to have it figured out this week. Well, I've just finished the exam this morning, so I'm hoping that this afternoon I'll be able to get that figured out. But so it will be moving from Friday until next week. I am going to be dropping some optional content, and I will let you know what it is that I'm going to be doing on that very shortly. One of the things I'm thinking about is probably dropping one of the small group activities so that we will have a week where there's not that extra thing to be doing, and so including in that week the extra, a little bit extra homework wouldn't be as bad. The other thing I'm contemplating with that may be if we still want to have that other activity, maybe having that one be entirely extra credit or something like that. So I will, as I try to figure that out, I'll let you know what's going to happen. As of 5 today, the exam is going to be released, due on Sunday. I have updated this morning the What We Know So Far post on Piazza. We have 3 components. We have the kinetic spreadsheet where it's going to be analyzing kinetic data to try to determine a rate law. The practice version is up on Blackboard and a YouTube video to take you through how to use it. There is a new version of the spreadsheet that will become available at the same time the exam becomes available. What you should do before you start the exam is download the new version of it, make sure it opens up and you can see things in it before you start the exam time, because you don't want to have the downloading and making sure it's up and running beforehand. There is a password inside it so that you can't see what the chemical system is you're working with until you type that in, and the first question on the exam gives you that password, so it will reveal all of the information about what the chemical system is. Yes? Yeah, they can't see. Oh. Yep, there we go. Is that better? All right. Thank you for pointing that out. Okay. So that's going to be the first third of the exam. The second third of the exam is about mechanisms, kinetic mechanisms. We've gone through quite a few examples of that over the last few weeks in class. It's going to be something very similar to that sort of thing. The mechanisms that you'll be looking at will be proposed mechanisms for the reaction you're studying in the first third of the exam, but you don't have to have the first third done correctly in order to be able to do the mechanism part of the second, for the second third. There are a couple of questions like at the end of it asking you to make a comparison between the two, but that's a very small number of points. It's mostly stuff that you can do independently of whether you've done the first part of the exam or not. The third portion of the exam is on equilibrium, and basically we have 2 topics there, calculations using ice tables and Le Chatelier's principle. Those are really the only concepts that we have within equilibrium. This is not going to be a single system in the equilibrium section. There are going to be, there's one equilibrium that there can be like about 3 questions on, and then individual separate questions about other kinds of things after that. So not one sort of comprehensive system there. Any logistical stuff to go into before we start talking some content? Okay, so we got only a couple of muddiest points on Piazza that have not yet been addressed. One of them was specifically about the kinetic spreadsheet and talking about getting negative K values on that. So let me call up the spreadsheet so that we can see what we're talking about with this. So if we go into exams, into here, the practice kinetic simulator spreadsheet, I will save it. We'll open it, and then in order to use it, you're going to have to tell the computer that yes, you want to enable editing. Oh, share screens. Yes, I will absolutely do that, and I'll show it here as well. Thank you. As always, be aggressive about telling me to do things like that. Here we go. All right. Okay. I'm going to stop sharing, then I'm going to reshare with the new one that's opening. There we go. Let's go back here. Now, okay. So we'll look at a sample set of data here. This is a first order example that comes up automatically with this. We will open up a new spreadsheet, paste the data in, and since we know it's first order, we'll go ahead and calculate the natural logarithm of it to validate the order. Let's go back at the top. And we will insert a chart. Okay, so we get a pretty nice straight line. If we were doing this for real, we would probably cut off some of the data here so that we don't have the noise down here and this one data point that's off. But to illustrate this question about the negative K, let me select our trend line. We come in here, display the equation on the chart. And what we see, if we zoom in here, oh, that zoomed in way too far, okay. What we see is that we have a negative slope, which you can see just by it going down. The thing to remember when you look at the linearized version of the integrated rate law for first order, the equation says that the slope is negative K. So when we see this value here of negative 0.0123, we take 0.0123 as the rate constant. So yes? It's sharing but not sharing. Okay, let me stop sharing. I will try sharing again. Oh, I know what it was. Since I had two Excel sheets open, it was stuck on the other Excel sheet. I apologize for that. Okay, so for the chat, what I was saying is if we were doing this for real, we would cut off the data somewhere around here so that we're not getting all the noise and the one data point here, that's obviously a bad data point. But even with it, without doing that, we can still see that we have a negative slope. And so the negative slope is because the linearized form of the first order rate law, rate equation, has negative K as the slope. So if people would like me to, I can go through how we see that. If people are comfortable with that, I don't have to do that. Question is what people would like. Okay, were you able to see it then a moment ago? Did it show up right? Okay. All right. Okay, well, I'm not seeing any requests. Can I go through an example problem? You mean which kind of example problem? Oh, for the Excel stuff? Okay, so sure. So what I would do, okay, here we go. We'll just do the whole screen. So what I would do is have something like, over in here, I would have some kind of rate law that you wouldn't be able to come in and see. So maybe it would be A plus 2B yields 2C, and maybe we have first order in A, second order in B, and maybe a catalyst D that would be something like 1/2 order or something like that. And then what I would do is give you some initial conditions. Let's see, so let's see how, so this is going out a long way. So let's set this equal to that. It's fine, and we'll say this equals that divided by 2,000 so that we can get data points. Well, that's no fun. Okay, that didn't work. So let's say 1E9. Okay, so we can see here that we have some kind of data. I would tell you the sort of starting conditions you would be starting with. And then I would say, okay, if you take this data, does it look like it's simple first order, simple second order, simple zeroth order, or none of the above? In this case, we can see that all of A, B, both A and B are changing simultaneously. So this one is not going to be a simple case like that. And then I would give you instructions to either use something like the method of flooding or the method of initial rates to determine what the rate law would be. And so based on the initial conditions, you would then decide how you're going to do this. So since I set this up here to have similar initial conditions, initial concentrations here, this one would be set up pretty well to do a method of initial rates on, because you could take it and double this one, you could take it and double this one, and so on as you go down. Whereas if instead we had this be something with some very large concentrations, and then this would have to be a much smaller kind of time scale, then this would be something that would be set up pretty well to do the method of flooding in order to find the rate law. Either one of them will work for certain types of rate laws. And so you would be trying to take the data and analyze the data to determine initial rates or determine rate coefficients from this, depending on which method you're using. Changing conditions, so if you're doing flooding, then you would change this to something else, to 1.2, get a different rate, change it to 1.4, get a different rate, and then do the analysis in a separate spreadsheet to find that information. Does that generally make some sense? I go through how to do those steps in the tutorial video. but the way the question would be set up would be very similar to what I just described. You would have an overall reaction, but you would not know what the rate law is, and you wouldn't be able to come over and look at it. And I would give you directions about where to start in terms of concentration so that you're actually getting some data on screen so that you can analyze it. And then you would be making the decision about what you're going to do in terms of changing the concentrations and taking more data in order to determine the rate law. General idea of how that's set up makes some sense? Let me go over to so question here, content videos, let's back up here. Okay, content videos about Excel, there's only the one walkthrough video covering it. Yes, there is only the one walkthrough video covering it. So in that one video, it's a pretty long one, unfortunately, but in that video, I go through both how to use Excel if you are completely new to Excel, and how to use it specifically for analyzing this data in this spreadsheet, copying data out into your own, doing what I did a moment ago to do this, to generate a first order plot, for example, and finding the lines so that you can get a slope from it and determine a rate coefficient from that. And that's the information you need in order to be able to solve this kind of problem. Lost the chat again. Nope. How do I get the chat back? I don't know how to get the chat back. Here we go. Okay. Can I do a method of flooding example? Okay, it's a lot to remember about all the different steps for each. The main thing about remembering what you need to do with these is to get yourself comfortable with selecting different regions so that over here, for example, if you want to plot, no, that's not what I want to do. So if you want to plot this column versus this column, which is what you need here, being comfortable enough with the selection of the regions in order to be able to get the two columns set. That's the biggest thing you need to do. So if you have the X's and the Y's selected, it's pretty easy to get the plot and then add a trend line to it to get your data. To get your rate coefficient. The tricky part, if you're not fluent in Excel, is how to do that selection quickly and efficiently. I go through that in that tutorial video, and I recommend practicing with this spreadsheet in a simple case. So set it up for simple first order, like this, which is what it comes up as a default, and practice taking the data, over to a new spreadsheet, adding a whichever version you're trying to check.
It's stuck on the first Excel page again.
It's still stuck on the first one? I'm so sorry. We will try this again. I have to remember to click screen rather than the window. Okay, so come back over here. So it comes up by default like this. So get yourself used to getting your data, copy, Control C, switch to your new sheet. Can you see this new sheet? Am I in the right place this time? Excellent.
Yes.
Paste numeric, put in whichever thing it is you're going to be checking. So it's relatively straightforward to do both of them if you wish to. Copy, end down over shift end up, paste, and you now have everything you need to check both first and second order. So you then select your X column by doing a shift end down, click, control click, shift end up to get this region, and you now can paste your chart and add a trend line to get your equation, get your slope. So this process here that I went through, I recognize that I am very practiced at doing this, and so it took me about a minute and a half to do this, to get that. With some practice, you'll be able to get this pretty quick, just by doing this, 8 or 10 times. You'll start to get used to the keystroke sequences that help you do this pretty quickly. So my recommendation is practice that some, getting to this stage so that you have that data enough that you're not stumbling over what it is you're trying to be doing before you start the exam. Okay, there was a specific request to do an example of the method of flooding. So I am happy to do that. To do an example of the method of flooding, we need to have, let me go back to the example I had earlier. We will do A plus 2B yields 2C, and we'll know ahead of time that we're going to be first order in A, second order in B, and half order in D. In the real case, you wouldn't know this. In order for there to be data, we need to have some B and D, I mean. So what I have here now is I have concentration A is much smaller than concentrations B and D. And so in this case, by the time all of the A reacts away, there will be no measurable change, no significant change in the concentration of B, so we are flooding the system here. So that's not the first, I'm sorry. Here we go. Okay, so we have the species A is at a low concentration, species B and D are flooded. And so what we would do here is select our data, bring it over, and I'm just going to make a new sheet to put this stuff in, and I'm going to put this down lower. Now, one thing that is kind of convenient that we can do is we can come over here and select this and just copy it in to identify, well, I'm going to give myself some extra room. If we insert, if I copy in the concentrations, then that's a handy reference as to what I was doing down here. And so if we plot, oh, I need to do the natural log. Oops, no. So if we insert our chart and we get our trend line, select our trend line and put our equation on, 3 significant digits is probably going to be enough, and we could put our K right here, so 0.0125. Now, what we would want to do next is say, let's modify one of the things we're flooding with and see what the reaction order is for this, this other component. So if we set B to 1.2 instead of 1, which is our, which is still flooded because it's still much higher than the A, copy it, bring it over here. We have a new set of data. In this case, it looks like we've got quite a few more bad numbers down below. So I'm going to truncate this down below. Insert a chart. Add a trend line. Equation on the chart. Okay, it's only showing me 2 sig figs there, so we probably want a little more accuracy on that. So we'll call this one now 0.0180. Okay, and bringing over the concentration set so that we can keep everything straight. Put that there. Once we have the numbers, we can get rid of the plots because we don't need them anymore. And let's do one more data point. It's usually good to have at least 3 data points to be able to see, is it looking like a straight line or not when you're looking at it. Take our data, copy, paste values, natural log, copy, paste. Got a lot of bad numbers here, so looks like about here would be a good place to truncate it. Insert a chart. Get our trend line. Find our slope. We've got 3 significant figures shown. So 0.0246. Copy in our concentrations. And we now have 3 data points. So let's see what our 3 data points are. We have our concentration of B, and we have our K. So our concentration of B is 1, 1.2, and 1.4. Our Ks in the same order are that one, and that one. And so now what we can do is plot these and see what it looks like. And what we see here is that it looks like there's a little bit of a curve, and even if this were a straight line, it wouldn't be going through 0, which is what we know this thing needs to be able to do if it's going to be a straight line. Because remember that our K observed is equal to our actual rate coefficient times our concentration of B to whatever power we have, times our concentration of our catalyst to whatever power that is. And so if this exponent were 1, then this would be a straight line that would go through 0, and it's clearly not doing that. So if we look on here and we try to put a straight line through it, it's clearly missing. So that suggests that it is something other than a straight line. So the next thing to try would be second order. Well, if it's second order, if the lowercase b here is a 2, if it's squared, then that means that we should get a second, we should be able to get a straight line if we take the square root of k. So we could take the square root of that, copy that down, and now plot these against each other. Insert a chart. And that does look like a straight line that goes through 0. So this shows pretty clearly that the reaction is second order in B, which matches what we set up in the first place over here on the rate law. So we can see that validated. In order to figure out what's going on with D, we would simply repeat the process. In that case, we would find that instead of it curving up like this, it would be curving down, which means that it's going to be less than first order. And so the natural thing to try at that point would be 1/2. Okay, I see the chat is blowing up, so I can figure out how to get back. Here we go. All right, so some questions here. If we know the orders already, why do we need to flood? Isn't flooding used to determine the order? Yes, and on the exam, this is exactly right. On the exam, you won't know the order. So I was setting up an example problem and showing you what we were setting up, and then we were going back and demonstrating that this process actually got us to the right thing. So do you always change B by 0.2 when doing flooding? No, it doesn't have to be 0.2. When I'm doing flooding, I tend to not double it too much because you never know when it's, if you might get into a different regime where changing it too much changes the behavior too much. So I tend to try to keep everything within about a doubling rather than doubling and then doubling again and so on. But it's not a hard and fast rule as to what you do. You kind of have to explore a little bit. Why not C since it's empty? So C we set up to be the product of the reaction, and the problem with this particular spreadsheet is that if we assign a reaction order to a product, and that product starts at 0 concentration, then we have 0 raised to whatever the power is, and the rate becomes 0, and so it doesn't work. In a real system, even when the product is part of the rate law, at the very, very first instance of the kinetics, it's not. And so that ends up changing very slightly in the first microseconds of what's going on. But this particular spreadsheet isn't set up to do that. So this equation looks like A plus B plus D goes to products. This was A plus 2B goes to products, and D was a catalyst. Will there be anything higher than second order, or we just need to find half order, first order, and second order? There could be 0th order, there could be negative order, there could be probably up to 3rd or 4th order are possible. It is easier to find the orders by the method of initial rates because because when you whatever the order is, you can find it just from 2 experiments. So rather than having to do 3 or 4 experiments with the method of flooding. So if I'm going to ask you to do something about using a really complicated rate law, I would almost certainly tell you to use the method of initial rates rather than the method of flooding. Why didn't we find A? So A, remember, is the one that was changing over the course of the reaction. And so it's really the only one that's changing measurably over the course of the reaction. And when we analyzed it, we saw that when we plotted the data, when we plotted natural log of the concentration versus time, we got a straight line. That by itself tells us that the reaction is first order in A, because fitting it in this way gave us a straight line when it was the only thing that was changing. Okay. Still, I don't know why I have such trouble getting back to the chat. Here we go. How do we know D is a catalyst? Well, in this case, we know that because I set it up that way. And so we came over here to the rate law, and we see that it has a positive reaction order, but it's not part of the stoichiometry, so it has to be a catalyst. In a real problem that I would give you, I would have these species identified as various things, and you would have what the overall reaction is. And if you see something over here that is not a reactant or a product, then it's a pretty good bet that that's going to be a catalyst or an inhibitor or a distractor. And so you would have to go in and test it to see what it actually is. Okay. I've seen a lot of examples of finding reaction order with initial rates using a small 3 or 4 experiment table that gives concentrations and rates. So why are we using all this Excel stuff when we could have used something simpler like that? Well, the issue is that in real life, that table has an entry in it that is the initial rate. That is not something that you can just read off of a machine and that you can just get. And in addition, when you have when you are given that table, you're not making the decisions about which experiments to run. And part of the goal of this is for you to be making those decisions so that you can so that you can demonstrate that you understand why you're picking different concentrations and then using them. So the idea with the method of initial rates in this case would be that, you know, if you whatever you start with, you then know that you come in and then you maybe double one of the concentrations, and then you measure the initial rate by fitting the first part of the curve, and that gives you that data point that would be in the table, but you're constructing the table yourself. So that's what we're going for here. Okay. Okay. There was the other muddiest point that we had actually dealt with the method of initial rates. So let me talk about that very briefly. Someone noted that that in the content video, I changed one of the concentrations for the second experiment, and then for the third experiment, I started from that point and then changed another concentration at that point. But then in the Excel tutorial video, after I did the second experiment, I reset to the first experiment and then changed one of another concentration. And so there was a question about what was going on there. So as an example here, if we have something like this, and so ignore the data at this point where I'm just looking at the concentrations right now. So in the content video, I did something like doubling this one, measuring an initial rate, and then I left it at this and then doubled that one. Whereas in the other video, I started by doubling one of them like this. I then reset it and then doubled this one. And so the question was on Piazza, does it matter what's going on with the difference in how we do it? The answer to that is that we simply need to have pairs of experiments where only one thing differs. So for example, if we have A, B, and C, and then we do so this would be, what on earth is that? Okay, we have this, and then the other case would be something like this. What we have in this case is comparing experiment 1 to experiment 2 tells us about A. Comparing experiment 2 to experiment 3 tells us about B. What we have over here is comparing experiment 1 to experiment 2 gives us A, then comparing experiment 1 to experiment 3 gives us B. All we need is to have pairs where we are only changing one thing. It doesn't matter which ones are the pairs, we just have to be able to have pairs. So both of the approaches work just fine, you just have to keep track of which combinations only have one thing that is changing. Okay. All right, if we don't get a straight line for A as we did here, do we flood other and set, say, B to 0.001 and then use that as the monitoring species? That would be a very good strategy. If you're told to, in order to use the method of flooding, you have to be able to extract a pseudo first order or pseudo second order or pseudo something order rate coefficient for the species that is varying, the species that you are monitoring. And so if you do the flooding and you didn't get a straight line for the natural logarithm, you might try it to see if 1 over the concentration gave you a straight line, in which case it's second order in A, but you still get a rate coefficient from the slope in that case, and you can still go forward that way if you want. If none of that works, then yes, trying something else would be probably a good way to go. I am not going to throw you a situation that is where you're going to be struggling to find a system that a set of conditions where you will where you'll be struggling to find a way to use the technique that I'm asking you to use. So if I ask you to do the method of flooding, it will be in a case where one of the reactants very easily can be identified upon flooding as can be identified as first order or second order. So example problems for Excel. So while this is, this spreadsheet here does not have a specific chemical system. What I'm going to be doing is giving you a specific chemical system with actual species that are involved here. And I'm going to tell you initially a set of concentrations to use for your first examination, and then that will be a set of concentrations and a temperature and such, where you will get a nice decay, a nice change in concentration that you can monitor, and you can start to evaluate it. And you can look at it just like we did copying it over directly without you having to modify anything over to something like this in order to see, is it first order, is it second order, is it 0th order, and so on. Then what I will be doing is saying, now that you have one set of data that you've been able to bring over, and you have a set of concentrations that you know have worked, I'm going to tell you one of the methods to use, method of flooding, method of initial rates, one of those two. And I will say, now find the rate law for this reaction. And so you would go through just the same kind of thing we did just now for method of flooding, if that's the one I asked you for, or a similar thing for method of initial rates. And so that's how the question is going to be worded. You know, what is the rate law? What are the orders with respect to each of the species is the way to put that. Oops, I'm going to the wrong place. Does the process change at all if the one you are monitoring is second order? No, it does not. The only thing that is different is that when you plot it, you're plotting 1 over concentration rather than natural log. You plot all the other, yes. So if you find that, if you're doing the method of flooding, and if you find that it works to do 1 over concentration, meaning that it is second order in the thing that you're monitoring, then all of them that you do would be plotted as 1 over concentration, and the slope would give you the rate coefficient. So I guarantee you that if you practice the method of flooding and the method of initial rates on example problems that you put in here, you know, picking some different orders, changing the rate coefficient, things like that. If you practice that in here, I guarantee that those are exactly the skills that you will be needing in order to address the first third of the exam. The one thing that we have not talked about that I mentioned in the tutorial video, but we haven't really done an example of it, is determining the activation energy. And so what you would do at that point, once you have the rate law, so let's suppose we do the whole analysis here and we determine that it is first order in A, second order in B, which we already did, and let's assume we go through the process and do the same thing for D to find that it is 1/2 order in D. Then that means that our rate law is equal to our rate coefficient times the concentration of A times the concentration of B squared times the concentration of D to the 1/2. What that means is that we can take, if for example we're doing something like the method of initial rates, we can take this expression and solve it for K. So, whoops, I didn't mean to delete that. Let me put that back. R equals K, concentration of A, concentration of B squared, concentration of D to the 1/2. Okay. So if we solve that for K, K is going to be R divided by that whole set of concentrations, right? So concentration of A, concentration of B squared, concentration of D to the 1/2. So if you determined these reaction orders by the method of initial rates, then instead of having the K's up here, you'll have R's, which are going to be the initial rates that you have. What you will do then is just say, okay, our K is going to be R divided by A times B squared times D to the 0.5. You put it in there, and if you've got some number here for R, that will calculate your K for you right here. So then, once you have your rate coefficient, and you have a way to do that once you know the rate law, come over here and you change your temperature. So you'll get different kinetics. Now this is a bad example because we don't actually have kinetics showing, so let's get back to the case where we're actually seeing some kinetics. So you see if we change the temperature, the rate changes. And so once you have this set up so that you can actually calculate the rate constant, remember that rate constant equals A e to the negative activation energy over RT. We solve that, if we linearize this, to have the natural log of K equals natural log of A minus EA over R times 1 over T. And so plotting natural log of K, which we just had, versus 1 over temperature, the slope of that is negative activation energy over R. And I think you've done some Newton examples of that kind of calculation. The difference here is that you'll be getting K's from these plots by changing the temperature right here. That's how that would work. So, is there an Arrhenius plot on the exam? That is certainly something that is very reasonable for there to be. So test opens tonight at 5, closes Sunday at 5, yes. How well am I expecting people to do on the exam? So my goal is to have an average of about 50 and a spread, plus or minus 30 in either direction from that. And the revised course grading scale is designed with that in mind, so that if I target that correctly, and that's the kind of thing that kind of grades that we end up getting, then the distribution of course grades is going to be pretty evenly split among CBs and A's. So that's kind of the goal on this. I definitely understand that the kinetics, the first kinetics portion of this is intimidating for people who haven't dealt with Excel very much. I will say that anything in science deals with lots of data, and Excel, once you get used to it, is one of the most important skills you can have doing anything with science. That doesn't have, it's not even just physical sciences, social sciences, environmental science, medicine. You're going to have more than you can handle with just a calculator, and that's why these are very important skills to have in any kind of science. But I recognize that that portion can be somewhat intimidating. The mechanism portion is similar to stuff that we have been doing for the last several weeks in examples in class. So I definitely expect people to do pretty well on that part. And the equilibrium portion of it, there are really just the two topics. There's doing calculations using ice tables, and we've done several examples recently that are pretty complicated ones, where we have lots of stoichiometric coefficients that are not one, where we have very large or very small rate coefficients, not rate coefficients, equilibrium constants. So we have to do a shift of the initial conditions. So we've done a bunch of examples with that. And the only other topic is Le Chatelier's principle, which we've also done a lot of stuff on as well. So my hope would be that, as intimidating as the Excel portion is, that 2/3 of the exam, which yes has nothing to do with the Excel portion, is going to be fully expected kinds of questions. Are there some questions that are similar to the practice sheet I linked in Piazza? Well, I linked up to about 5 or 6 different practice sheets that I found. And I actually haven't seen Emily's, so I don't know. So I don't actually fully know. Are we doing anything? Let's see. So what I would suggest is look for the equilibrium portion, look for equilibria that have stoichiometric coefficients that are other than 1 in examples, and practice some of those. For kinetic mechanisms, I think some of the practice sheets I linked to were kinetics as well, and there are some mechanism examples in there as well. So those are pretty good. Le Chatelier question here, are those going to be qualitative or quantitative? Well, Le Chatelier by itself is by its nature qualitative. If you're doing an equilibrium calculation that is quantitative, it's going to be an ice table. There's no getting around that. Le Chatelier tells you which direction it goes, but that's about it. Now, that's extremely useful information, because you need to think about if I modify a system in a certain way, how is the reaction going to shift? It's very important to be able to do that. But there isn't really anything quantitative about Le Chatelier by itself. And when you're thinking about Le Chatelier, I do strongly recommend, in most cases, thinking about the reaction quotient as being products over reactants, and when the reaction quotient shifts away from equilibrium, you think, is it bigger or smaller? And then what happens to the numerator in order to get back? That's the easiest way to think about it, because if the reaction quotient is too big relative to the equilibrium constant, then that means too much numerator, which means too much product. So it will shift the other way. That's the easiest way to keep track of it, is to think about the numerator. Is the process different for half order? So we have not come up with a way to, we have not derived a way to just plot some modification of concentration versus time and find it's linear and know that it's half order. The method of initial rates is very straightforward to get half order out of. There's one thing I do want to show briefly. I'm going to stop sharing here. Go back to the document camera here. It's tempting to look at these method of initial rates and say we have one concentration and we double it, and then we have 0.36, and then we end up doubling to get 0.72 for the initial rate. And so, oh, it's first order because it does the same thing. It's better in some ways to think about a more generalized way to do this so that you're not having to rely on recognizing that you're doubling and you're doubling. Okay, so if we have the initial rate under conditions 1 over the initial rate under conditions 2, and the rate constant's the same, and everything we're not changing is the same, so they cancel. And so we only have our species over our species under conditions 1, under conditions 2, raised to some power, and that is that A, that power that we want to know. So it's a very quick way to do this is to pull the A out and now take the natural log of both sides. So natural log R0 over R02. I'm gonna have to switch pins because I'm running out of ink. Equals A times the natural log of A1 over, or A condition 1 and A condition 2. And so you can find your exponent by doing the natural log of the rate under conditions 1 over rate conditions 2 over natural log A1 over A2, whatever concentrations you picked. So if you're dealing with something where there's some noise in it, so it's not going to be perfectly, double or something like that, just plug it into this formula here, and you'll plop out what the order is. And if you end up with it being like 0.98 or something like that, yeah, that rounds to 1, so it's first order. But it could as easily come up being 0.49, which would tell you that's going to be half order. So, so this is a foolproof way to find the reaction order by the method of initial rates. And that is an advantage that the method of initial rates has over something like the method of flooding, because there is a very, very straightforward procedure you can follow to get whatever the order is. Okay, and we're pretty much out of time. Any questions, anybody? Okay, so I am planning again to have extended office hours most of tomorrow and most of Saturday. So I will post my link to Zoom, and I will probably just be sitting at my computer doing work if nobody's there. And if somebody shows up, great, happy to help. So please feel free to use that. I will post to Piazza my link for it. My recommendation for taking the exam, if you are scared of the Excel portion of it, which I think you don't need to be all that scared of it, but if you are, Start on the second third, and then do the third of it, because they don't rely on it at all. And that way you'll get out of the way the stuff that doesn't depend on that part. Okay, thank you very much. What are the hours? Oh, for the online office hours? The extended office hours? I don't know exactly yet. It's going to depend on how much I need to catch up on sleep, because I didn't sleep last night getting the exam ready. But I will definitely post when I know what the hours are likely to be. It's probably going to be from about, I would guess, 10 till 4 or something like that. Yeah, probably each day. So some pretty extensive lengths.